Hello. So today this is the FOC brushless BLDC controller. I'm using two PCB board for the servo. So there's an H bridge on it. I'm using one half of it, so that's three half bridges, and controlling three of phase of the motor. And here I'm using a GD32 microcontroller. So now I can have position control. And for the algorithm, originally I was using simply the sine function, so that's sine theta, and like there's ABC three phases. For A it's sine theta, for B it's sine theta minus 120 degrees, and for C it's sine theta plus 120 degrees. And after getting the result, I plussed 1 and divided by 2, so that's converting the sine function is from -1 to +1, and we can only have 0 to 1, so that's shrinking the range of the function, and then times the PWM period to get the trigonometry output. But after looking on Google, I found that the sine control, is not using the maximum efficiency. It's only 85%. So there's an algorithm called SVPWM control. And I have implemented it, but now the problem is the algorithm is kind of noisy. I'm not sure what causes the sound. It's a very sharp sound on the motor. But now it's kind of working. This is the oscilloscope of the two phases. Now it's probing the signal control. So you can see now I think it's 0.3 duty cycle, like 30% duty cycle. And the typical SVPWM, if you observe it closely, when for example the blue line here, when it approaches here, it will first reach a maximum and then fall back and then reaches the maximum again. So it's like bouncing. Let's do it slowly. Now it's reaching maximum, bounce back, and again. Actually this is one full revolution now. Yeah, you can see it pauses here for a while. Yeah, that's SVPWM. And yeah, the current for 30% duty cycle is 0.5 amps. Well, the limiting factor is really the H bridge. I don't want the H bridge to handle too much of a current. And now I can control the motor pretty well. So if the acceleration is too big, it will lose steps because it's open loop. But in general, it's functional pretty well. And the next step is add two current sensing resistors on these two lines to probe the current. So that's current closed loop. Yeah. And now let's see the code. This is the code. these six steps are used for the high speed, so basically the square function. And for low speed, we are using this function. And in main, we first initialize USART for serial communication, and then we are using ADC to get just an potentiometer connected. And here it's for a timer. We need 6 pins. Pin A8, A9, and A10 are the for high speed, high side controlling. So it's connected to the high side of the MOSFET, of the H bridge, half bridge, yeah. And B13, 14, and 15 are the complementary output. So we are using timer 0. It's the advanced timer. Align mode is center aligned. And prescaler we are using 0, so that's the highest frequency, 108 megahertz. Period we don't need to set it here. Clock division is 1, like maximum. And output state, for initialization we want to disable the output. And polarity, it's high. So note here, polarity high for the complementary means that it's the outputting the inverse of the regular channel. If here we input low, then it will be the same as the regular channel. These two options I'm not really sure how, what's the purpose of it, so I just leave it low. And we initialize channel 0, 1, and 2 of timer 0. The auto reload value I'm using 4098, so that's 0 FFF. I don't know, because if I input here a higher value, meaning a longer period, the current of the system will actually increase. I'm not sure how, what's the principle behind. So this is the optimum value for now. This is the output mode, PWM 0. And same for last video, this line is very important, it's easy to forget. And finally, enable timer 0. Send a trigger to ADC so to start the conversion. And here configure, enable all the outputs of the PWM timer. Send ready. And here I have several test functions. So the first one is just read the value of the potentiometer, convert it to angle, and then feed the angle into the function. And others are just various testing. So so for angle we are using radians here. And let's see the function inside. This line is convert angle to single rotation. Yeah, because this angle can be multiple rotations. And for the inner function, we really want to use just one rotation to determine various things. So here, this function, these 3 lines are actually basically just modulate for the modulate function for floating points. So if this were the integer value, we can just use angle equals angle modded by, for example, full rotation 360. These two are the same. And then, these three lines are modulation. And for this one, because we can only, the while loop only works for positive angle. So if we are having negative angle, we need to convert it to positive just by adding 2 pi and minus the angle. Yeah. And here we convert it to single rotation, and we define an alpha value, because for the SVPWM we are defining a six regions for a single rotation, used by A, B, and C coils. So we need to the alpha angle is the relative angle inside one section, and here we further convert the full rotation to the relative angle inside each section. This line is pretty similar to this one, just we divide it by 1/3 of a pi, so 1/6 of full rotation. Yeah. And then we have T1 and T2. This is the vector component of the resulting vector. I need some graphs to explain. So for the document, I'm using this article. Yeah, here. We are just separating the target vector into, for example, these two vectors, and T1 and T2 are the time for each one. Yeah, just like this. Well, actually the link is here and for reference, just like this is a website. Yeah. I don't need to explain more. And what we're trying to get is to get the width of the ABC coil, like in this part. The middle one is T7 here. It's the half of the full null cycle, the non-forced cycle. And this part is the weaker vector of the resulting vector, and this one is the stronger one. And the area here and here is the another one half of the non-forced cycle. And then we combine the times into the into the pulse width. Yeah, pulse width of the PWM signal. So there's PWM A, B, and C. And for each section in the for each section we have different algorithm to get the A, B, and C. It's pretty similar to the square cycle one, the A high, B low, A high, C low, blah blah blah, that one. And finally we set the pulse width to the timer configuration, and now we get the, yeah, that's pretty all. So yeah, duty cycle in that example it was 0.3. Yeah, I still need to fix the noisy thing and add closed loop control.